Alright, so let's go through the try yourself 2, which is a 2020 A-level question. So this one is the long question, 20 marks, paper 3, section B. Okay, so for first part A, right, state what is meant by an inelastic collision between two objects by reference to the speed of the objects. So for this, you just need to say that the relative speed of approach is not equal to the relative speed of separation. So for the inelastic, I always remember kinetic energy is lost if it's an inelastic collision. So it's lost as internal energy, sound energy, etc., etc., and it cannot be recovered. Okay, so for part 2, the kinetic energy of the object right before collision will be greater than the kinetic energy of object after collision. Yeah, so that is for the first part A. Okay, let's move on to part B. How do we actually solve this question? So we have these two spheres suspended by threads, right? So I displace sphere A, which has a mass of 0.96 gram. And the mass of sphere B is m. So the vertical distance of the support is about 150 centimeter. So I displace by 21 degree. We are asked to determine show that the horizontal speed in which each strikes sphere B is 1.4 meter per second. So how do we actually solve this? This one is actually we need to use a bit of the PCOE, the principal conservation of energy. So imagine that I displace the sphere A to some height. I don't know what's the height lah. So I can actually calculate the height based on the diagram, right? So looking at the diagram, right, you can see that for sphere A, I displace 21 degree and I can actually draw like a right angle triangle. So I want to determine, I know that the string right itself is about 1.5 meter. So what I actually want to do is actually to calculate what is the adjacent. Adjacent is the so-called vertical dotted line that I show on the screen. So it's about 1.4 meter. How do I get 1.4? Very simple. You simply just use Tuakaso, right? So you want adjacent, you got hypo, so you use cosine 21 degree equal to adjacent divided by hypo. So if you do the calculation correctly, your adjacent should be 1.4 meter. So the sphere B, okay, now let's just say I release the thing, right? The sphere A will, before you hit the sphere B, right, will have a speed of something which I want to calculate. So I need to determine what is the height that I actually raise sphere A. So the height actually is 0.1 meter. So I hope you can see the thing. So at this point, right, you simply just calculate what is your GPE. So GPE is equal to mgh. So m is your your mass of the sphere A, 0.096. G is 9.81, then H is 0.1 meter. So when you do the calculation, your GPE will be roughly, let's do a okay, your GPE roughly will give you 0.094176 joules. Okay, then I release it, right? Before I hit sphere B, all the GPE will be converted to your kinetic energy. So I simply just use the idea of the GP equal to KE, the loss of GP equal to the gaining kinetic energy. So let's do the calculation. So half mv square equal to this, right? Then you just need to manipulate. You should get 1.4 meter per second. So that is this part. That is how we actually do this part. Okay, so let's move on to the part C. Okay, part C, now we have the sphere in part B colliding, right? So sphere A rebound with a speed of 0.79. So sphere B move off with a horizontal speed V, which I don't know. So during the collision, right, 14% of the initial kinetic energy is transferred to other form of energy. So meaning that the 14% of the initial kinetic energy is converted to internal energy. So we are asked to calculate what is the momentum P of sphere B, the magnitude. Okay, so this one we simply just use the principal conservation of momentum. So before collision, right, the total momentum. So this is the momentum of sphere A. This is the momentum of sphere B. So apparently the sphere B I don't need to calculate because it's stationary. So you just put 0. So sphere A you can calculate to be 0.096 multiplied by 1.4 meter per second. So the momentum before collision of sphere A, right, will be 0.1344. Okay. So what about after collision? After collision, they say that sphere A rebound with a speed of 0.79 meter per second, meaning that you need to include the negative sign, put a negative sign to it. No? If not, yeah, then the calculation will be wrong already. Okay, so the momentum of sphere A, right, after collision is this mass times velocity. So this will actually give you, let me calculate, 0.096, right, times negative 0.79. So the momentum of A after collision will be negative 0.07584. Then for sphere B, there's some momentum because they say sphere B move off with a horizontal velocity V. So I put momentum B. So you just need to solve. So for example, right, how do we actually solve? So before equal after. So before is 0.1344. Aftermath, right? Aftermath will be due to sphere A, negative 0.07584 plus the momentum of B, right? So it's just B, PB lah. So P moment, B of moment, the momentum of B will be 0.210 kg meter per second. So that is how we actually do part I. Okay, let's try part 2. So we are asked to calculate the kinetic energy of sphere B. So how to actually do? Okay, first we know that 14% is so-called loss as internal energy. So what is left is actually 86% of the kinetic energy of sphere A. So I simply just use this idea, then I can solve already. So okay, first 86% over 100, right? You multiply by okay, so my kinetic energy of the initial, okay, so half mv square. So my m is the 0.096. So my speed, I can quote the part B answer. So just 1.4 bracket square. So this will be the kinetic energy left. Okay, multiply by 0.96, 1.4 square. So the 86% of the initial kinetic energy will be 0.0809088 joules. So of course this remaining kinetic energy that's being left will be the kinetic energy of sphere A. Not just that, will also be the kinetic energy of sphere B. Then of course the 14% is being lost as the heat energy. So what is the kinetic energy of sphere A, right, after collision? So this one I know, right, because I already know my speed. So half 0.79 meter per second. So 0.0809088, right, is equal to kinetic energy of A plus kinetic energy of B. So this KEA plus KEB, right, they are the kinetic energy after the collision. So okay, kinetic energy A will be half 0.96, then V square is your 0.79. So I don't need to include the negative because I squared, then it will be positive lah. So I just need to calculate what is the kinetic energy B. So 0.0809088 is equal to 0.596 times 0.09 square. So this will actually give me 0.0299568 plus kinetic energy of B after collision. So kinetic energy of B will be equal to 0.0809088 minus 0.0299568. So roughly your kinetic energy will be 0.050952, or you can round off to 0.0510 joules. So that will be the kinetic energy of B after collision. Okay. Okay, so let's move on to part D. So using your answer in part C, right? So to determine what is the horizontal speed of sphere B, and of course, eventually what is the mass of your sphere B. Okay, so with this, I can actually use, right? Okay, so for part part C answer, is it part C? Yeah, part C. Okay, we know the momentum of sphere B 0.21, right? Okay, so I can put first P equal to mv. So my P will be 0.21. Then for kinetic energy, half mv square, so Ke of B is equal to half mv square. So Kb is 0.051. Okay, so how do I actually determine my speed and whatever, right? So I can actually use a bit of shortcut. So for example, kinetic energy I can equate to the momentum, so P square over 2m. So this is a very useful formula, I can relate kinetic energy with momentum, so it's a bit of shortcut. So kinetic energy will be 0.051. Then the P square, right? P square I can put 0.21 square. So I can, okay, of course I calculate the mass first lah. So the mass, okay, it's good. Okay, so it's 0.051 times 2, right? So roughly what you will get is 0.102 m. So this will give you 0.21 square. So m will be 0.21 square divided by 0.102. So the mass of the sphere B will be roughly 0.432 kg. Okay, so of course I solve for part 2 first. I just put here 0.432 kg. Okay, how do I actually solve for the speed? So after I know my mass already, I can just put inside. So P is equal to mv. So my momentum is 0.21, right? My mass is 0.432. So my speed, I can use 0.21 divided by 0.432. So this will actually give me a speed of, horizontal speed of roughly 0.486 meter per second. So that is how we do the calculation, right? Okay, so now for part E, state and explain during the collision, right, between the two spheres, is it possible for both spheres to be stationary at the same time? So 3 marks, right? Okay, of course the first mark will be the state, whether will it be stationary or not. Then the 2 marks will be the explanation. Okay, the stating part is simple. You simply just say no. Okay, why is that? Why can't both spheres be stationary at the same time? Because apparently at the initial momentum is equal, the total initial momentum is equal to roughly, okay, let me just quote the answer first. Okay, so initial momentum P 0.096, okay, 1.4. Okay, it's about okay, sorry, get the answer already. 0.1344. So this is initial momentum is 0.1344. So that is the very second point. So the third point, how do we explain? Just say that according to PCOM, right, the total momentum must be conserved. Total momentum of system must be conserved. So if both spheres are stationary, right, at the same time, the total momentum of system will be equal to 0. Which will cause the PCOM to be violated, because apparently you can see that the initial momentum is not equal to zero. So that is how we actually explain. So the total momentum of system is equal to zero. So which is not equal to the initial momentum. Hence, the PCOM cannot be violated. Okay, so that is for part E. Okay, part F, calculate the magnitude. So this one is just give them the number of the impulse, meaning that this one you want the delta P of sphere A during the collision. Okay, so so delta P is equal to final momentum minus initial momentum. So my final momentum, my initial momentum I know already, so it's about 0.1344. Okay, final momentum, because they tell us that the sphere A, this sphere A, move off with a speed of 0.79 meter per second. Let me just double check first. 0.79. So I rebound with a velocity of negative 0.79 meter per second. Then I just calculate the momentum. So the momentum is mass speed, right? So my mass is 0.096. My velocity is negative 0.79. So as I calculate my change in momentum, 0.79. So my change in momentum in overall will be roughly negative, delta P, negative 0.21024. Round off to negative 0.210. So of course, just give them magnitude. So delta P is equal to 0.210 kg meter per second. So this is 0.210. So for part G, we are asked to refer to the direction of the impulse in part F. So the direction of impulse you can see is negative, meaning that the change in momentum is towards the left hand side. So explain why the initial speed of sphere B has to be in the horizontal direction. The center of the sphere are on the same horizontal level at the time of collision. So we must understand one thing is that by PCOM, right, the delta P, the change in momentum of the system must be equal to zero. So the PCOM states that there shouldn't be any change in momentum. But of course, how do we actually relate to explain why the center of sphere are to be on the same horizontal level? Because, imagine that we have this sphere. So this is sphere A. Okay, so this is the center, right? So this is the speed. Let's put it speed like that. Okay, for sphere B, is like this. So example, let's just say the center is right here. So this is sphere B. Okay, what you realize is that the center is not aligned on the same horizontal level. So what happens is that if this situation arises, right, sphere B will not move on horizontally. It will move at maybe a diagonal speed. Let's just say like that. So in this particular case, the PCOM will be violated, because if you move diagonally to the horizontal, right, I can actually resolve the diagonal vector to be to the vertical and the horizontal. So with this, right, apparently there shouldn't be any vertical momentum. So there's no vertical momentum. There's only horizontal momentum. So I simply just write, for part G, delta P of system is 0. So that is the first mark. Second mark, I just say, the momentum. If the sphere A collide with sphere B, if the center of sphere A collide with sphere B, with center of sphere B not at the same horizontal level, this will actually cause sphere B to have a vertical momentum. So if it has a vertical momentum, then the PCOM will be violated. Because just before you collide, right, there shouldn't be any vertical momentum. That's how we actually explain this question.